My name is Tim. I am the co-author on a textbook. This talk will maybe be a little different than some other talks at JuliaCon. I will definitely be discussing use of Julia, but moreover, I will be discussing how to display Julia and use Julia to display things. This is the book, Algorithms for Optimization, came out in March. It's a general broad overview of a bunch of different optimization algorithms. I'm not going to talk about optimization specifically, but more what Julia was used for in this book and how we used that to then solve different problems in the actual development of this textbook. There are a lot of problems that you have to overcome when writing a textbook. So things like just how do you typeset it? How do you generate figures? If you have code in your book, how do you make sure that it's correct? How do you present algorithms? It's a very fundamental question. And then there are a lot of things that we did around compile time automation. How can we get the book to build things for us when we compile rather than having a bunch of side assets that we keep track of? So in this talk, what I'm going to do is I'm going to talk about all the different problems we faced. And for each problem, I'm going to tell you what kind of the naive strategy or the baseline strategy is. I'm going to tell you what the status quo tools are to solve it, and then what tools that we used are. And at the very end, I'm going to show this again. We're actually releasing a template repo that has every single thing that I'm talking about that you can take, download, follow the install instructions, and you can then write your own textbook with exactly the same format that we did, because there's a lot to keep track of. All right, so the first problem is I want to write a textbook. How do I take what I've written and get it to look like a textbook? So very fundamental issue. Many of you may have already solved this. The traditional workflow for writing a book is as follows. You have like Microsoft Word or Google Docs. You type your stuff up, and then separately you have a bunch of figures. Maybe these were generated by Julia or MATLAB, or you drew them or something. You bundle it all together, and you then hand it over to your publisher usually, who then takes it and has professional typesetters make it look professional. And then they, in the end, have a PDF that they print. This is not very efficient for multiple reasons. One is that the author has less control over the look and feel. But even more important than that is any design iteration is really long. So if we have some sort of look and feel we want, we pass it to the typesetters. It can take months before they get back to us with a change. So we want to avoid this. So we actually did this. This is a little uncommon. All of our resources are in .tex files. We compile it, we get a PDF, that is what they print. So there was no professional typesetter anywhere. I guess we were kind of the professional typesetters. And that meant we controlled everything. You get some additional benefits here too. Notably, everything can be stored on Git. Every single figure in the book is generated during compile time. And so you don't have to handle all of those separate figure files that can get out of date because they get regenerated every time. And so if you change one parameter, everything's consistent, everything gets redone. Cool. TeX is the file format for LaTeX. LaTeX is a professional typesetting system. If you haven't used it, it's super, super common for academic papers. But it turns out you can use it for books as well. The LaTeX document class that we used is the Tuftybook class. It's actually pretty fantastic. So this is one page on our book, 296. The Tuftybook class has a main area for text, and then it has a big side margin in which you can place things like side comments, side figures. You can have bigger figures that stretch across. And then here's like a Julia function that has a side caption. And the nice thing about this is that your main text contains the main flow of your book. And then if you ever need to interrupt the flow, you put those things on the side. So any like side comment that's not in line with the main track of thought goes on the side. So this is what we used. Some other concepts from Tufty. Edward Tufty is known as like the father of data visualization. One concept that he has is this concept of small multiples, which we use throughout the book, where if you're trying to show something evolve over time, you don't want to have different images. you want to have as similar of an image as possible over time so that you can easily pick out the differences. So we use techniques like this throughout the book in order to show, in this case, the evolution of Nelder-Mead on an optimization function. Cool. All right, so first problem is typesetting, and then the not so obvious tool, or sorry, the very obvious tool that we use is LaTeX, but maybe the not so obvious tool is the TuffDebug document class and the fact that we can use Git for the entire source control. All right, so we decided we're using LaTeX. What language do we write our algorithms in? This one will not surprise you. Okay, so first, most people use pseudocode. If you pick up a random textbook and it has algorithms in it, it's almost always pseudocode. Why? Because it's usually terse, and it's usually easy to understand, and it's language agnostic. So you're not assuming that your reader knows this particular language. There are big problems with this. First off, it's not real code. So there's no guarantee that if I take this algorithm, I can actually translate it into something that runs. Side effect of that is, as the author, I can't guarantee that my code works, so I can't even test it. So I'd like to use a real language and avoid the ambiguity of pseudocode. We thought of trying different languages for a very short amount of time. Obvious problems with all of them. So C++, very clunky type system, very verbose, too low level. MATLAB costs money. It's common and vectorized. Python is also a common choice, but again, the math is cumbersome, requires vectorized operations. So we use Julia. You all know Julia. I am going to belabor this, however, because I think it's important. So Julia's type system is fantastic. So we do use types in the book, but we don't have to. So we use types where it's necessary, but in order to show algorithms in a compact and easy to understand form, we often just drop types, and then we let users, well, A, the code runs either way, and B, you can often infer what the type is based on the symbol that we use. We can use generic functions. This is really nice. We can just pass in things like f and gradient of f into some sort of optimization routine. This is used all over the place. Numerical operations are built in. What that means is math looks like math. If you take this same function and you try to write it in something like Python or C++, it's going to explode and you'll have no idea what's going on. But with Julia, it's really nice. This is also really nice for things like Unicode. So for instance, nabla for the gradient operation. If you're doing things with like normal distributions like mu and sigma, super convenient. And we can leverage it throughout the textbook. And that's what I show here. So again, we have nabla, we've got delta, epsilon, Unicode, math looks like math. Here I have a comparison between pseudocode and C++. So on the left is the despot algorithm, which is an algorithm for decision-making theory. Usually when you show it in pseudocode, you show it in a way such that it's easy to understand and it's kind of terse. So here we have 3 different despot routines, and the C++ code is on the right side, and it is massive and very difficult to follow. Julia, however, the same code looks almost identical. And so one function here, one function here, one function here, one function here. And so what we get from this is that Julia is already very close to pseudocode in that it is already easy to understand and terse. The advantage is, though, it's real code and it actually runs. Okay. There are JuliaCons. Julia is an evolving language. The book, we started writing it in Julia 0.5 and we had to take it through all the way to 1.1. There were some hiccups on the way. We dropped some packages going to 1.0 because the packages weren't updated to 1.0. But overall, it's actually worked out fairly well. There are a few hiccups, a few wishes we still have, one of which is this argmax idea. There's a GitHub issue for that, but Julia is pretty fantastic. All right, so what language do we use? Julia, clear win. All right, the remaining problems are, I think, a little bit more innovative and kind of the main point of the talk. So we've chosen to use Julia in LaTeX. How do we typeset it in LaTeX? You can go with a fixed width font. This is just using the verbatim package. It looks fine, but really boring. No syntax highlighting. You can jump to the listings package, which is perhaps the most common way to do things. In our case, it totally messed up our font. You get some syntax highlighting. I didn't spend a lot of time trying to make this look prettier, but what we ended up using is pigments. Pigments is a fantastic package for algorithm typesetting. You get syntax highlighting, and things look really nice. This was not nice enough for us. So Pigments had a lexer and a style for Julia 0.5 and I believe 0.6. But as we move forward in time, it kind of got out of sync with Julia 1.1, and there were some corner cases where certain symbols weren't recognized or certain things weren't formatted correctly. And we didn't really like this green and blue format. And so we actually used Pigments with a custom lexer and style in our book in order to give us the same kind of color consistency that we already have with everything else. And then also catch all of those corner cases with Julia 1.1 that weren't caught by the 0.6 lexer. And so our book has Pigments plus a custom lexer and style that all runs when you compile your LaTeX document. So the problem of algorithm typesetting was handled by Pigments with a custom lexer and style. Cool. All right, more exciting. Compile time automation. So I don't want to have to generate any figures by hand separately from hitting compile. Moreover, books often have examples. And so here's an example of an example from the book. So we have like f of x equals sine of x squared. We evaluate f of x at pi over 2 and get a value. The derivative is this, and then we run some Julia console stuff. I could type this up by hand, like do, right? However, maybe tomorrow I decide maybe I didn't want to evaluate this at pi over 2, but I wanted to do pi over 3. I would then have to go get my calculator out, figure out this, retype it in, figure out this, retype it in, and then retype all this stuff in. I don't want to have to do that manually. I really want the program to do that for me. And so to the rescue comes Python Tech. So I can actually have, here on the left, we have the LaTeX code that gets executed, and on the right we have the result. And so I can do traditional math typesetting, so like f of x equals sine of x squared, which shows up here. But I can also do evaluation. So this /jl will run sine of pi over 2 squared, and it's then going to produce that 0.624266. Similarly, this Julia console block is going to take each line and it's going to evaluate it as if you're running a Julia console. And so I don't actually have to type in 0.624. I just get that as the output of real of v. And so this prevents your examples from going out of sync. And if I have an algorithm that I'm running from my actual code that I've typeset, I can run it actually in these sorts of environments. So if I change my algorithm, I can get a new result, and I don't have to remember. I can just say, oh, I updated my algorithm, I just need to recompile. And it's all automatic. Same thing goes for typesetting. So typesetting is done by Python Tech, by Pigments, but that's called by Python Tech. And so if I have an algorithm block, I just say Julia verbatim, type up an Elder-Mead algorithm, hit compile, and then on the right, I get this same kind of typeset algorithm block, all through that same package, all through Python Tech with Julia. Cool. All right. Oh, and this algorithm environment is this kind of gray rectangle that we have around the outside. Okay, so compile time automation. If I hit compile, I can automatically execute Julia code, and I can automatically typeset Julia code. Super useful. I can also do Julia consoles environments. All right. This book is full of figures. I believe it has over 300 figures in the book. All sorts. There are different ways to make figures. None of these figures are their own separate files. All of these figures are defined in the .tex files. Some of the figures are created by hand in something called TXE. So TXE is a language specific in LaTeX for creating figures. It's a lot like SVG. So I can create a TXE picture. I can say, okay, draw an ellipse, then draw a blue arrow, then draw a red arrow, and then fill a circle. And when it compiles, it gives me a scalable vector graphic embedded in my document that looks like this. So for simple figures, I can do it by hand, even for some not so simple figures. However, when it comes to plots, I don't want to be making plots by hand. And so to the rescue comes something called PGF plots, which sits on top of TXE. And this is still LaTeX, so this is still in my LaTeX document. But now I can create an axis, I can add a plot, I can add different other lines at different coordinates, I can set axis parameters, and I can get something that looks consistently like a plot. with labels and other things. It's pretty powerful. But even this runs into limits if I'm doing something complicated. And furthermore, if I have an optimization algorithm, I would really like to not have to hand create my figures. I'd really like to use my optimization algorithm and then plot kind of what it is doing. For multiple reasons. One, because that way I get rid of a lot of work because I get the optimization algorithm doing the work for me. But on the other hand, I can also inspect and see, is it even doing what I want it to be doing? It's kind of like a way to do debug. And so Python tech, which executes during compile time, I can use to run Julia code that will generate these figures for me. And for that, I use pgfplots.jl. So pgfplots.jl is a Julia plotting package for pgf plots. And juliaplots.sty is an integration with LaTeX, such that in my code, in my LaTeX code, I define Julia code here. That's very similar. This is all Julia stuff. I produce an axis. I can plot it. And then when I do the /plot my figure, it will then show up in my LaTeX document after I compile. All right. So it's a little nested. I'm writing Julia code in LaTeX. When I hit compile, Python tech takes this, produces a .tex file, and then the /plot inserts it back into my document. So the second time I compile it, I get that same figure in my document as if it were a .tex file. Okay, so here we have, let's see. We have 3 different linear plots, and then we just have kind of, so 3 different linear plots with kind of like labels. So nothing too crazy. That gives me this. I certainly would not want to have to type this up by hand. And on top of that, this isn't just running, this is running the algorithms for like complex forward and central derivatives that I have defined elsewhere in my Julia code. And so if I change those, this plot will also change. So it's all tied together. So this is a very simple plot, kind of shows the base case, but I've got some more complicated ones. So for instance, this plot, you don't want to do by hand. But here we have some like wolf conditions and like descent method conditions that are all automatically computed and visualized for us. I wrote code that does this, but it runs the actual stuff under the hood when I hit compile. This is a covariance matrix adaptation running on a function. And we can see, hey, it works. And again, I wouldn't want to have to do that by hand. pgfplot supports images, so this is pretty cool. We can get contour plots. And so this is a really simple Gaussian processes for different kernel lengths, but we get all sorts of cool things. Again, none of these files are actually in the repo. It's all .tex files, just in my main LaTeX code. All right, so figure generation. We can do some things by hand with TXE or with PGF plots directly, but moreover, most of the plots are done with pgfplots.jl that executes during compile time to produce TXE or PGF plots. So it's a pretty cool ecosystem. And that saves a lot of time because I've got one place where I define things like colors, and if I change them, everything has the same style. If I change like one place, then all of the labels have a different font size, and it's all consistent, which makes it very nice. All right, so the last thing is testing and code coverage. I'm writing a textbook, and when people say textbooks, they don't often think about testing and code coverage, but I mean, we're doing code and algorithms, and so it does make sense. So how do I take these .tex files and how do I test my algorithms? Well, one way I've already talked about is I'm using the algorithms in the plotting, and so if the figures look right, then I'm happy. But that's not really enough. I want to actually kind of test these algorithms, maybe put in specific test cases. So I defined a new Julia environment, Julia test, in which I can write just straight up Julia code. So here, for instance, I can get POMDP tuple for my machine replacement problem, and then I can run this algorithm POMDP value iteration, and I can test that I get the actions that I expect for different beliefs. This is straight up Julia code. When I compile my LaTeX document, nothing happens. This is totally ignored. However, I've got a separate script that can run through all of our source code, and it finds these Julia test blocks, pulls it out, puts them in a separate file, and it does the same thing for the algorithm definitions and put those in a separate file. And so now I have a Julia module that contains all of my module source code, and then I've got a test file, a test script that I can run through, and I can make sure that all of these things are correct. So I can actually put that on GitHub, and I can make sure that that triggers every time I commit. And then we can make sure that our build passes with Travis CI, just like you would with any other Julia repo. And I can get code coverage with coveralls, just like I would with any Julia repo, except it's textbook code. And so that's really nice. I can also export all of our figures to iJulia notebooks. We did this at the end in order to then give the iJulia notebooks to professors so that if they're teaching from the book, they have the exact same code that generates the figures, and they can edit them or tweak them or show them in class. And again, this uses a script that parses our source code, pulls out the algorithm chunks, and puts them into iJulia notebooks. And it's all automatic without going away from having an all-text repo. So it's just .tex files, basically. So that's testing and code coverage for the book. Mainly, this is provided by custom extraction scripts. And then we hook into the traditional Julia infrastructure of Travis CI and coveralls. Yeah. All right, so we covered a lot of tools. So LaTeX, which hopefully you've all heard of, but more specific things like TuftyBook. We are able to leverage traditional things like Git, but then there are some more like specific things like pgfplots.jl and juliaplots.sty that we developed ourselves. But I don't want you to have to remember all this. And so as I said earlier, we have opened this up. So Tufty Algorithms book on the Sizzle repo. Sizzle is the Stanford Intelligent Systems Lab, is the research lab I'm from. Has a base template for a textbook that has all of these tools available. It has installation instructions. You can take it, you can download it. It has examples in it, and you can get up and running. Recommend using it in research papers as well, Python Tech to generate figures, not just textbooks. So yeah, thank you very much.
We have about 8 minutes for questions. Please just feel free to come up if you have any questions.
This is a fabulous book, by the way. Really beautiful.
Thank you.
Yeah, first I want to say everything looked really great. And I wanted to know, how long is the average compile time when you build your book?
Oh, that's a great question. Yeah, okay. So if you compile the full book from scratch, it's about 45 minutes. And so if I push to the repo, it'll take that long for the book to compile. In development, I almost never compile the full book. Yeah.
You can compile it incrementally? And
Sure, yeah, so I'll just compile one chapter at a time, or I can even compile a section at a time.
if you don't mind, I have one more question. One major, complaint that I see a lot is that plots in particular takes a really long time to run the first time. When you run these things in I forgot what it was called, PyTech, or however you're running the Julia code, is it one continuous runtime where I generate one figure and it has then basically precompiled plots, and then when I generate another one, it uses the precompiled version, or does it have to pre-precompile?
That's a great question. So Python Tech, it does something under the hood so that if you don't change the source code between compile runs, it will know not to rerun that figure. So it only redoes it if you've changed the text in that field.
But I mean, if you have two figures in the same chapter and you run it, does generating the first picture compile all of plots and then the second picture compile all of plots again, or can it reuse?
I think there's one Julia session per file.
Okay.
Yep.
Cool.
And that's why, if you've defined an algorithm up here, you can use that algorithm down here. You can specify not to do that, but that's the default. Yeah. Good question.
Okay, so can you have more than one Julia session per file?
Yes.
Okay.
Yeah, that is possible.
Another question, is it possible to hide some Julia code? I mean, maybe you don't want to show the libraries you're using or something like that in order just to illustrate an algorithm. You don't have to say, using, I don't know,
Oh,
whatever.
man.
Yeah.
Yes. So, okay. So you can do that. There are actually a few cases where I did that in the book. And I didn't talk about that here, but the code that extracts the algorithm, I have a special set of flags that I can set in comments before the code block that can do replacements when I extract it for testing. So yes, we pack that into our custom extraction scripts. So it is possible.
Okay, and it's all in the repo, all of that stuff.
So that feature should also be in the repo, but it's not documented, but I can document that. Yeah.
Excellent. Thank you.
Yeah, because there are some cases where you want to switch like one line or something. Yeah.
Yeah, hi. So I'm also working on a book, and I struggle a lot with finding the right tools, so it's interesting to watch this. So far, I have opted to choose a documenter that does some of the things here with testing code and so on. Did you ever consider using that, or and if not, what did you pros and cons versus using LaTeX?
I guess I'm not very familiar with Documenter. I think we used it for one.
Documenter.jl, that package that's used in for the Julia kind of standard documentation packages.
I think we integrated that with one repo in our research lab, but I was not involved with that.
Yeah, maybe it was not existing when you started.
It definitely did not exist when we started, but it's more recent. Are you generating a textbook with that?
Yeah, that's sort of like going trying, but I might not end up doing that.
Okay.
Yeah, but you can write Markdown, so I thought I can switch tools maybe later.
Okay. Yeah. I'll have to look into that. Thank you.
First of all, I went through the book. It's really, really good. So thank you for that. I had a question which is basically related to, you showed that one function where you try to do argmax on f of a.
Yeah.
Would it not just be easier to just introduce the reader here to simple broadcasting for those kinds of things? Have you had any thoughts about that?
To introduce simple broadcasting for this? Yeah. So I can generate a special function for it. Mm-hmm. So actually I have. So I use underscore argmax, but it'd be nice if it just worked. But yeah. Yeah. So there is a GitHub issue for it. I think the main contention is whether you return the index or if you return the actual value. And in my case, I want A. I don't want the index of A. And I think there's some ambiguity with generated functions, but yeah, it's definitely something I can work around. Thank you. Yeah. Hi, Chris.
Hey, I'm very glad you made the GitHub repo. Mm-hmm. I'm curious if you're going to use it for your new book. Also, I'm going to give you all my questions up front.
All right.
Also, question I'm curious what the size of your PDF was at the end, because you're not putting any images in there. And also, I also wanted to, even though I'm just be a little bit greedy, so that if suggesting the use of Documenter or something like that, which could in the end put some comments into your notebooks. I love the notebooks, but I guess I'm even more greedy, hoping that they could have some little bit more informative comments.
Okay. All right. Let's see if I remember the question. So how big is the book? So this book, we just released a new version of it, is 13 megabytes. That's all 520 pages, which is, I don't know, is that big? I guess that's big. And that's because it does contain figures, but they're figures after compilation. Right now, the iJulia notebooks are literally only like a chapter header. I think there might be a section header, and then the pasted code. We do have captions for every algorithm in the book that there's no reason why we shouldn't also just take those and put them in for some sort of documentation. And then maybe it's worth in the next book to include additional details. So thank you for bringing that up. The other question you asked, if I'm remembering them all, is are we using the same strategy for the second book? And yes, I'm working on a second book with Professor Kochenderfer on decision-making theory. The kind of answer is yes. And the other kind of technical side note is what we're releasing here, Tufty Algorithms book, is exactly what I'm using for the second book. And it's actually a better version than what we had for the first book. So things like Julia test didn't quite exist. It was a little different. And so I've changed it around based on what I learned. And so you're actually getting the better version in this. Was that everything? Okay, good. Remembered them.
One more question?
Sure.
How did your publisher react to your new method of creating your book?
Okay, so our publisher is MIT Press. Let's see, I guess, so it's not common for the authors to directly produce a PDF. In our case, it worked out really well. Professor Kochenderfer had already published a book with them not using this method. So they already knew that he was a very responsible person, but they were willing to try this out. I thought it worked really well. There were a few cases of us having to figure out, oh shoot, how do you actually like typeset that the way they want in LaTeX? But that was all figured out. And that's all in here. And yeah, so we still had the whole design iteration cycle of, oh, we'd rather that you change all figures from figure colon to figure dot. And for us, that's just a one-line change we can do. And so yeah, I'd say it was overall very good. Yeah. Cool, thank you.